Hi, and thanks very much for inviting or giving me the opportunity to come here and give this talk about my work. And I've enjoyed very much all the talks that have been going on as well as the posters. Thank you for having me here, so I enjoyed that as well. My collaborator is Pradeep, and he's my PhD student. He's off now on a postdoc, and he's done most of the work. I'm reporting it, and so I'll be talking about functional motifs in a protein family. The proteins I will consider as a string of amino acids, and the motifs are a cluster of these amino acids, these functional motifs, and I'll be considering a family of these proteins. The system that I'll be dealing with is the Beta-Lactamase family, which is an enzyme or a protein secreted by bacteria in response to antibiotics like penicillin and bacterial cephalosporins. And these beta enzymes hydrolyze the amide bond of the beta-lactamase chain and make the antibiotics inactive. So here's the active penicillin, and when you put in the enzyme, it hydrolyzes this bond and makes this inactive. So our plan will be actually to find out what motifs are there, or which clusters of amino acids are present, so that we can target those clusters and deactivate this enzyme action so that the penicillin is active. So we do this by actually, not by an experiment. Those experiments are very difficult. We look at the data that we have, that there is, and in the protein data banks, and this is one of the data banks, and it consists of these beta-lactamate families of class A, B, and there are 547 protein sequences. So, we need to, so there's a sequence of proteins, and which are made of amino acids, and they're taken from different organisms. Okay? So this is bacteria, and you're taking some different organisms, and the amino acids are different in some cases, and in some cases this chain are the same. So we do some sort of filtering, and we can reduce the number of protein sequences to 559, and the length of this protein, these amino acids, is 248. So we put it in a multiple sequence alignment, which means that the greatest number of similar characters fall into a column. So we align it. Then various people in the literature have actually put frequencies at each point. That means the frequency of this amino acid A, how many times it appears in each column, and have replaced this multiple sequence alignment with the frequencies. But what we did was actually look at the properties associated with each of the amino acids, the hydrophobicity properties, and created this data vector. So this is due to the hydrophobicity, and this is the polarity of each of the amino acids. So one can define a covariant matrix, okay, of the frequencies, okay, where the Fy is the frequency of having an amino acid A at a position I. Or one can, and then Fij is the frequency, joint frequency of having a position, of having an amino acid A at I and B at J. And this is the usual definition of correlation frequencies. And you sum over all the amino acids and find a final correlation matrix like this. These gentlemen in Ranganathan et al. In Cell have done this analysis. But of course, we have not looked at the frequency correlation matrix, but the Pearson correlation matrix, in which we replace each of the elements by the property, the hydrophobicity or the polarity or the volume, and calculate the Pearson correlation coefficient in the usual way. This is the this is the element in each of the data matrix, and we subtract the mean of each column and form the covariance part and divide by the standard deviation. Okay. We also build another matrix, which is by putting at each of the correlation, at each of the points in the matrix, random data taken from distribution which has 0 mean and standard deviation 1 sigma. But the dimensions we keep as S, and the length is L that we got from the protein correlation matrix. And these are just the Wishart matrices, and they have been studied very, very rigorously in the random matrix literature. And the bounds are given by bounds of the eigenvalues are given by these terms, and these bounds can be found when the ratio S over L, which is called Q, is greater than 1. And for this particular SNL, lambda plus the edges of the eigenvalues are lambda plus given by the small one. So in the system, the eigenvalue distribution is given in this way, and the shuffled or the Wishart ensemble eigenvalues are distributed in this way. So, and what we do is actually look at the eigenvalues which are not bounded within the two endpoints of the Wishart ensemble or shuffled matrix, but those that are outside it. And those eigenvalues carry the most information. In particular, we notice that for these insets tell you the eigenvalues which are near 0. And so we look at the eigenvalues which are outside this, the least eigenvalue, in the random case. So, and these are the eigenvalues outside it, and they're about 13 number. And the ones that are outside for the large eigenvalue are about 14 number. We'll focus here on the largest eigenvalue and its corresponding eigenvectors. So we do the usual random matrix process and find that the spacing distribution of these eigenvalues after unfolding, etc., is almost the same as the GOE. But this is the case for the data matrix that we use. But for the properties. But for the frequency-based ones, the spacing distributions are not quite the spacing distributions that one finds for the GOE. Similarly, well, when you look at another, if you look at another statistics, that is number variance, you find that the string is more like an uncorrelated sorry, correlation matrix, whereas the property-based correlation matrix is more like the GOES. And these are the distribution of the eigenvectors, and I should go on and because I have 2 minutes left, and come to this slide in which I'll look at the entropy of the eigenvectors. And these are the eigenvectors at position I, and it's the jth element in that eigenvector corresponding to the eigenvalue I. And this is a graph in which on this axis is the eigenvectors arranged in the ascending order, and this is the entropy. And we find that in the string-based, so the frequency-based, the entropy is all, it's quite random. But for the hydrophobicity-based, you see that there's a distinct preference of information from the lower eigenvectors. And here is the square of the eigenvector components for the lowest entropy sites. And we find that the contributions are only from the positions 38, 41, etc. The largest eigenvectors are given by this red, and they don't seem to, they are not localized, whereas the smallest eigenvalues are localized and hence give a very clean value. In the string case, that is not true. There's a lot of, so here we have those numbers, and this is in the real space. And these are the the important positions that we found in those sectors. And this is in the real, one of the enzymes, beta-lactamase. And if you go to the literature and find the experiments, you find that this corresponds to the conserved motifs. And similarly, you can do the eigenvector 2, and you find very nice correspondence between experiments. There are some other eigenvectors which don't have identifiable roles. And I'll go and show you this figure in which this is actually the protein in which the sites are labeled, and you see that they are very close in the 3D. So I won't go through the network because I'm out of time, just to show that the same sector comes out in the network analysis at threshold 0.8. But an important point from the network analysis is that you can find which node is connected to which. We've done the same problem with many other proteins.
After lunch, maybe.
Oh yes, I'd love to. Yeah, thank you. Yeah, I just wanted to make a comment that there's a lot of work happening by Coco and Monasan and White on these type of models in CNS, and of course the Princeton guys are there.
So let's thank Nivedita and all the other speakers once again.
Chairing this session.